Welcome to the course of analysis of several variable. So in this lecture we will start module 4, which is partial derivative and directional derivative of several variable functions. And we will start with the partial derivative. So section 4.1 is partial derivative of several variable function. So let's define the partial derivative. Let omega be an open in Rn, and a1 a2 an is in omega, and then we have a constants f is from omega to Rm. Then we have k equal 1 to n. We say that f is partial derivative with respect to x n, or you can say xk at a if we have the limit x tends to ak, the function f a1 a2 xk an minus the point where we are taking the partial derivative in x minus ak. This exists in Rm. So if this limit exists in the Rm, because f is a function from Rn to Rm, so this f a and this point will go to Rm. So therefore, if this limit exists in Rm, then we say that f has a partial derivative with respect to xk, the kth variable. We denote this limit by del f del xk at the point A, or f suffix xk at the point A, and some cases also dxk f a. Different books or different manuals have different notation. Well, so in this example, we are going to check if the given function is partially differentiable at the point a is equal 0, 1, and with respect to y at the point 1 minus 1. Let's see what is the function. The function is given as is defined from R2 to R, and given is like this: fxy equal x3 minus 2yq over x square plus 5y square in xy not equal 0, and 0 when xy equal 0. Now we'll check it that it is differentiable at partial derivative exists at 0, 0 and 1 minus. So before doing that, we just take it the definitions. We will recall the definition. So fxab, this can be written as limit h tends to 0, a plus hb minus f of ab over h. Same way, fyab is equal ab plus h minus f of b over h. So this is partial derivative at the point a, b. So now in this case it is 0, 0. So a equals 0, b equal 0. So fx 0, 0. So f of a is 0 minus f of 0, 0 over h. So if you see the function, so this will become h to the power 3 over h square minus 0 over h. And then we simplify it, you will get the value is 1. So the partial derivative of f at the point 0, 0 is 1. Now let's check the partial derivative with respect to y. So again, f y 0h is equal to f limit h tends to 0, f 0h minus f 0, 0 over h. So now in this case, what we'll have from the given functions, we'll have here f0h is equal minus 2h to the power 3 over 5h square. F0, 0 is 0, and then h. So if you simplify it, you will get it minus 2h to the power 3 over 5h to the power 3. So h to the power 3, h to the power 3 will cancel out, so it will be minus 2 over 5. So finally we have the conclusion that the partial derivative with respect to xy exists at 0, 0. Now the second part is it says that we have to calculate fy1 minus 1. So here we are trying to define a little bit a different way. So this can be written as limit y tends to b f of ay minus f of ab over y minus b. So thus f of 1 minus 1. So this will be a equal 1, b equal minus 1. So this will gives you 1y minus f1 minus 1, and denominator is y plus 1, and the limit is goes to y tends to minus 1. Then we systematically solve it. F in the f, just replace x by 1 and y as it is. So you will get 1 minus 2y to the power 3, 1 plus 5y square, and then this one will become 1 plus 2, 1 plus 5. That means it is 3 over 6, so 1 over 2. And then we further simplify it. So you will get it in this form: 2, 1 minus 2y to the power 3 minus 1 plus 5y square, and denominator is like this. Now we'll try to get the limit for this. So for that we separate it, that which is not a problem in the denominator. So this part we separate it, and here is a problem. We have y tends to minus 1, this denominator will become 0. So we'll try to solve it in different way. So here we got a directly limit. Here we got a directly limit from this part, and then this remaining part after simplifications will have this part. So clearly you will see that this is 0 over 0. So we can apply L'Hopital rule, and then we'll have this form: 1 over 12, and then it will be minus 10y minus 12y square over 1. And then put y equal minus 1 and simplify it. You will get the answer as minus 1 over 6. Okay, now we have few notes. Note 1 is that if we take x equal this from Rn, and then partial derivative of f with respect to the variable xk at the point A can be written like this formula. This is standard formula. Okay. So now we'll substitute it here: xk minus ak equal t. So this implies xk equal ak plus t. So t is just a variable. You can substitute any other variable also. So now we'll put it x k equal ak plus t, and then replace it in this equation. So after that, what we'll get? The derivative of f with respect to xk at the point A is equal, this x will replace by ak plus t. Okay. So remaining is same. Then we will get it here. So now our task is to write this part. So this part can be written as a1, a2, ak, an plus t 0, 0, 1, 0, where 1 is the kth entry of the vector. So therefore, we got it here: a plus t ek. So therefore, this vector can be replaced by short form a plus t ek. So we can rewrite it, this vector, as limit t tends to 0 f a plus t ek minus f a over t. Okay. Now we have the second node. In this node, we will take the point A, and then partial derivative of f with respect to xk at the point A. So then we calculate all this. Means to whom, with respect to which variable you are doing derivative, you have to keep that as a variable. Other point you can substitute it the value of the point. Means in this case x equal ak, means x1 is equal a1 a2 ak an, x2 is equal a2 a1 a2 xk plus 1 xn. Okay, now we have note 3. This is that if the function f, capital F, has a component of functions f1, f2, fn, then the partial derivative of capital F with respect to xk exists if and only if all f1, f2, fn have a partial derivative with respect to xk. Note 4 is that if partial derivative is belongs to Rm, then f dash a is linear from Rn to Rm. Now with this we have examples here that find fx230 partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to g, while f of xyg is this function. So this is easy function, you can solve it directly, but here I will give you one technique to solve it uh, and convert it almost the ordinary derivative. So in this case what we have, fx230, we can write it del x of fx30. So if you remember, we have a note in this slide that the to whom with respect to we have to take the derivative, we can keep this as a constant. Now what will happen, that fx30, so we'll substitute it in the function, and then we will get it del x, x e to the power 3 multiply 0 sine x dot 3 dot 0. So therefore we got it here. This is become x and this is 0. So therefore we will get del x, x 0, and now partial derivative of x is 1, so we will get it 1 0. Now this is partial derivative with respect to x. Now what about with respect to y and with respect to g? Now with respect to y, again we substitute the value of x, value of z, and y is constant, so it is as it is. So therefore, if we take the derivative here, so this is we have to calculate at the point y equal 3. Now here you will see that f2y0, we have this function, so we will put it x equal to here, y equal as it is, and g is equal 0. So therefore you will get it here x e to the power 0, x e to the power y 0. So and here it will get it sine 2 y 0. So we got this point here, that del y to 0, which is gives us 0 0. So this is the answer. Now move to the next question. Next part of this, fg230. Now we have on g. So this is now given as del g of 2 e to the power 3z sine 6z. Because if we put 230 here, so you will get it here. X is 2, y is 3. So it will be 2 e to the power 3z. And then here it is, you have sine x is 2, y is 3, 6g. Now if we take the derivative here, so this will give you 6 e to the power 3z, and this is 6 cosine 6z. So after simplifications, putting the value of g equals 0, you will get in this form 6 e to the power 0, comma 6 cosine 0. So the final answer is 6 6.